The point about watches is that they all go together. Now, if this much better watch, the thing would happen, if I move one up, okay, wait a little bit, 1, 2, 3, 4, and I come down, they would not indicate the same time anymore.
This is Verona, an Italian city of timeless beauty where history and art have danced through the ages. It's also been home to Renaissance thinkers who defied the science of their times with outlandish theories on things like how diseases spread and how long the Earth takes to spin around the sun. And centuries later, scientists and thinkers around the world are still trying to pierce through the mysteries of our universe. Great thing about this job is you get to meet really interesting people doing amazing things, and sometimes you even get to meet one of your heroes. I'm in Verona and I'm about to do just that with Professor Carlo Rovelli, well-known physicist and world-renowned science communicator. There he is. Just a small warning before we go on. The conversation I'm about to have isn't for the uninitiated, but if you're a little obsessed with the joy of science like we are, we think you'll enjoy it. Professor Carlo Rovelli has spent his life trying to understand physics and explain it to the world through his best-selling books. Professor Rovelli, as I've been reading your books, it seems to me the history of science is a series of intuitions by people who had no right to be able to come up with the intuitions they did in the times that they lived. Does that sound right?
So there are these towering figures that make incredible jumps ahead in our understanding of the world, and we're amazed by them, which is true, but we tend often to forget that each one of them come out from a field of knowledge and discussion. So the Archimedes, the Einstein, the Newtons, the Darwin are really a product of a large debate.
You talk about Anaximander, for example, to the point I was making before. He lived in a time where everybody, well, they didn't even think about this stuff. The idea that he was able to come up with the sky is all around us, it's below us, that we live in a sphere that's floating in the ether, I suppose he thought. It seems incredible that he could take that, well, quantum leap in understanding.
It is incredible. It's even more incredible if we consider the fact that nobody else has done that. First of all, in India and China, in Africa, in the Americas, there were huge civilizations, wonderful, rich, fantastic, with incredible richness of creation and thinking. And everybody always, in all these civilizations, thought that the universe, the cosmos, is down this earth and sky is above. And he understood, just with his mind and his culture and his openness, that that's not the case. It's true that the sky is up and Earth is down, but Earth is just a big stone, so sky is all around it. And how he got there? Well, by being open, by being smart, by looking around, by listening, and by changing the way of thinking about reality. It's a breaking point in the history of human thinking.
If we jump a long way ahead, Richard Feynman, he's one of the greatest physicists of the 20th century.
Yeah.
Now he says, including himself, no one really understands quantum mechanics. Is that true?
Quantum mechanics is a strange theory. It's very much fashionable today. Everything is quantum because also we have the first quantum computers that work. We have a lot of technology which is quantum. Our cellular phones are full of quantum little technology inside. And quantum mechanics is not modern physics in a sense. It's 100 years old. It was born in 1925. But unlikely other major discoveries like Maxwell electromagnetism or Einstein relativity theory, quantum mechanics has some incomprehensible aspect on it. Quantum mechanics says if you do that, this will come out. But if we try to see what is really going on, try to get a picture of what's going on, we're completely confused. And Feynman pointed this out.
But once again, quantum mechanics, if you're just someone like me and our viewers who are living in the world, it is completely counterintuitive to our experience.
It is.
It is the opposite of our experience of life. And we've found that that is the basis for our life.
Yes, it's very counterintuitive what happens. But look, when Anaximander figured out that the Earth is a stone floating around, isn't equally counterintuitive? Why don't things fall? You come from New Zealand. How could people there live upside down? I mean, how can you live like that all the time, right? With your feet
taxing.
up and your head down. It's very strange. You New Zealand people are very strange. The first time we encounter this idea that the Earth is a stone that floats there, and there are people all around it facing different directions. People in Beijing are like that, and people in the US are like that, and you people in New Zealand are upside down. I mean, it just makes no sense at all. It cannot work. We think that's universal. Up is up for everybody, down is down. No, up and down change depending on where you are. And in quantum mechanics, we're still in the process of digesting what we have understood. I mean, we grow up thinking that humans are completely different than the other animals. And then Darwin comes along and slowly convinces all of us that we have common ancestors. It's fantastic. It's beautiful. It changes completely our rearranging of things. I guess what I'm saying is that it's wrong to think that there's a natural, intuitive way of thinking and then there's a scientific one. It's a continuity. When Einstein did relativity, that's exactly what he did. He had the Maxwell equation and understanding the electric magnetic phenomena, and it wouldn't work unless you realize that time works different in different parts of space and time. So he abandoned the idea that time is the same for everybody to make better sense of what we know. And that's the way fundamental science works.
James Clerk Maxwell was a physicist in the 1800s. He came up with some groundbreaking equations on electromagnetism, which led to the discovery that the speed of light is constant for all observers, regardless of their motion. But Einstein realized that this challenged the traditional idea that everybody experiences time in the same way. He theorized that if you're traveling in a certain direction, and if your speed approaches the speed of light, time will actually slow down for you. This is known as time dilation, revealing that time is not absolute, but relative. And that's what helped him come up with his theory of special relativity, E equals mc squared, revealing the profound relationship between energy, mass, and the speed of light, a connection that shook the very foundations of physics.
The standing on the shoulder of giants, it's an expression that was already used by Newton. It's definitely a cumulative effort.
But for Einstein to go, okay, these equations don't work, I need to throw time away.
It's spectacular.
That's the only word for it, isn't it? It's spectacular.
It's spectacular, yes. It's astonishing. Einstein was working at the patent office, as we all know, in Switzerland, in Bern, and was asked how to synchronize the clocks in the different train stations so that trains could move around with a common timetable. Because of course, in the past, without trains, when people were going by horse, you didn't need the clock to be synchronized in Paris and in Bordeaux, right? So he was working about this clock synchronization. And then he realized that if you take physics seriously, the Maxwell equation seriously, you just cannot synchronize clocks. And he has the astonishing courage of saying, look, if I drop the idea that time is common for everybody, that everybody has different time, which is a marvelously new idea, I understand better the physics.
So he said that time is relative.
He says that we have this idea that there's a present, now, okay? You and I are talking now, and now in London something is happening, in New Zealand something is happening, on the moon something is happening, on a different galaxy, in Andromeda something is happening, which is the same time all over the universe. Well, that's not the way the universe works. The universe works with a temporality, things happen in time, in a much more complicated way. The question what is happening now in Andromeda is a meaningless question. If the Andromedan people send a message to us and we reply, there is millions of years, because light takes time. Even you and I, right? I see you now, you see me now, but think for a moment. I see you means that light comes from you to me, which takes a millisecond. But that millisecond, it's real, it's just very small, so we can forget about it. But if you think about it, I see you in the past, and you see me in the past. So we're having a conversation in which each of us see the other one in the past. You live in your own time, I live in my own time, we send signal to one another. Can I borrow your watch?
Yes.
Just the point about watches is that they all go together, okay? Now, if this much better watch, the thing would happen, if I move one up, okay, wait a little bit, 1, 2, 3, 4, and I come down, they would not indicate the same time anymore. Why? Because it's actually more time passes here and less time passing here. Today we have in the laboratories very good clocks where this can be measured. So if you go up here, there's more time, and down here there's less time. So time passes at different speed. And in fact, near a big star, or even near a black hole, it goes much, much, much slower. So you can walk near a black hole, stay there for a little bit. You stay there 1 minute for you. You come out and a century has passed outside.
Basically, according to Einstein, time can slow down or speed up because of things like motion and gravity. Near massive objects like Earth, time runs slightly slower than in outer space. And that affects a lot of things some of us take for granted in our modern lives.
I have a story. The GPS, when the first satellites were put out there by the American Army, the physicists told the engineering, careful, because time there goes a little bit faster. So your clocks there are going to be faster. So the generals that were supervising all that were reading these things and saying, oh, come on, time goes faster. I don't believe that. So the first satellites were actually really put up there with a switch that could or could not take into account this effect. And if you don't take into account this effect, the difference of speed of time up there, the entire system does not work. So, the Einstein theory was exactly right.
Einstein's theory of special relativity, which showed that time is relative, was published in 1905, also known as his miracle year. That's because in that same year he published his theory of general relativity as well as 2 other major papers. One of them, on the nature of light, is why he won the Nobel Prize.
In the same envelope in which he sent his paper, where he worked out these things about time, in the same envelope there was another paper, nothing to do with that, okay, about electromagnetic waves and light, in which he had this idea that maybe light, electromagnetic waves, is little by little packets of energy, okay, photons. And that's why he got the Nobel Prize. He didn't get the Nobel Prize for what we were just talking, relativity times gravity. No. He got the Nobel Prize for understanding that light is made by photons, which is the first steps toward quantum mechanics.
So he was also the father of quantum mechanics.
Yeah.
Photons, these individual packets of light, are also known as quanta. And they're what quantum theory is based on. The idea that energy comes in discrete lumps. But Einstein didn't stop there.
And in the same year, in that same envelope, the third paper, nothing to do with quantum mechanics, nothing to do with relativity. He just used the fact, an observation, that if you have a liquid and you have little grains of particles, or if you have air, which is a fluid, a little grain of dust that floats, they move in a very funny way. Okay, it's called Brownian motion. They move sort of randomly. Okay, and you can compute how much they move. He realized that this is due to the fact that they're atoms, molecules. Okay, so they hit molecules, and from how much they spread around, he could compute the size of the molecules. And that's really what proved that atoms are real. Up to that point, early 19th century, early 20th century, the idea that matter is made by atoms was not really accepted by physicists.
In one envelope, special relativity, quantum mechanics, and proved that atoms actually
That's
exist.
right. That's right. I mean, it's hard to believe.
But he's the father of quantum mechanics.
Yeah.
But then later on, quantum mechanics gets, to quote him, in one particular case, gets too spooky even for him.
Absolutely. There is a conversation he had with Heisenberg. Heisenberg is really the one who makes the click about quantum.
Heisenberg's most renowned contribution to physics is the uncertainty principle, which tells us that we cannot precisely know both the position and the momentum of a subatomic particle at the same time. It's almost as if things at the quantum level are built to be fuzzy and unclear. So what is it that Einstein couldn't get about quantum mechanics?
In classical physics, we say, oh, it's very easy. The particle is here, then it's 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 here, and then it's there. So we can reconstruct. Quantum mechanics, we cannot do that. The calculation we have is that the particle is here, then it sort of spreads in a cloud of probability, and then it can get here or there. But in between is nowhere. And if we think that it's somewhere, we get confused because if it is here, something would not happen.
So this is that idea that once you observe a particle, a subatomic particle, you change the outcome of the experiment.
Yes. The view of quantum mechanics, which I prefer, which I think is more reasonable, which I think is going to be more useful, is that it has nothing to do with observation, with us. Okay, we are just part of nature, like everything else. The point is that the property of the particle are always relative to something else. And we are confused if we make something absolute. Let's go back again to the up and down, right? Up here is different from up in New Zealand. If we think that up is up and we forget that it's relative to where we are, we get in trouble because there's no universal up. If you think that the present is the same, it's not relative to where we get in trouble. We don't understand special relativity. And I think we have trouble in understanding quantum mechanics because we tend to make things absolute. The particle is here, period. For the universe, for God, forever. No, the particle is here with respect to the screen. With respect to something else, it's not there. It may have no position at all, because position is always when there's an interaction related to something else. That's my understanding of quantum mechanics. But you see, it's deep, because it challenges our very idea of what is something real. Something has properties not by itself, but with respect to something else.
And famously, Einstein's general relativity, special relativity, and quantum mechanics tell us different things about the universe. They can't really be reconciled. Is that correct?
You bring me home here to my major reason of interest and passion in science, which is exactly that. The Einstein extraordinary and certainly successful understanding of gravity and space and time, general relativity, on the one hand, and quantum mechanics on the other hand, which Einstein triggered and then was developed by others, which also is something we know is true in the universe. We cannot bring them together in a consistent way, or more precisely, we can, but because we have tentative theories. One is loop quantum gravity, in which I've worked all my life. The attempt to bring together these two great advances of the 20th century, Einstein general relativity and quantum mechanics, and to understand the quantum aspect of gravity, which is the quantum aspect of space and time.
That space-time has quanta just like every other field.
Yes, that's exactly the core of the theory. And loop quantum gravity is sort of the mathematics to describe this quanta of space. When light arrives on my hand, so here is the light of the sun that arrives on my hand, okay, and it's light arriving here from the sun. But if we look carefully, and it's easy technologically, it's just a lot of individual photons arriving, grains of light. Well, space as a whole, the space in which we are inside, that's what Einstein understood, is a gravitational field, is a field. It's a field like the electric field, so it's also granular. So space is granular.
But these grains of space are far smaller than any other particle we know about, correct?
Oh yeah. We're many orders of magnitudes smaller.
Exactly how small these quanta are can be hard to imagine. Let's begin with something we can easily understand, the human hair. An individual hair is 100 micrometers wide, and a micrometer is a millionth of a meter. At the level of individual hair cells, we're beyond the resolution of our eyes at around 10 micrometers. As we travel ever inwards, we soon cross the boundary where the human imagination starts to get a little blurry. At the level of atoms, we're using picometers, or trillionths of a meter. Beyond the electron orbitals of an atom, we still have a very long journey before we reach the nucleus. And its component protons and neutrons are measured in femtometers, or 1,000th of a trillionth of a meter.
So in particle physics, atoms are very small and nucleus are very small. Inside nuclei were the quarks, which are very small. We are talking of things millions and millions times smaller than that. So the granularity of space is at a scale where a proton is like a galaxy.
And what will we need to see for us to understand that, yes, that's true, that space is granular? Experimental or observational? How will you prove it finally? You and others.
Well, the way of doing that is the old usual way of science, right? So how did Einstein convince everybody that space is curved and time is curved and all these things happen? Back in the early 20th century, there were no clocks measuring at that precision. There was not. How did he convince everybody that that was reasonable? Well, by working out with the theory some phenomena that were not expected, not predicted before. So what I'm working on right now is trying to understand what happened in black holes. Black holes are very big phenomena, very strong phenomena, and inside black holes, quantum mechanics must matter. So it's really quantum gravity, what happens inside black holes. And black holes live very long time, but not forever. They evaporate, they become smaller and smaller and smaller. It's a quantum phenomenon. And when they're very small, again, it's a quantum gravity phenomenon. So with my colleagues, we have computed what happened using loop quantum gravity, and we have this prediction that a black hole becomes a teeny white hole, and the hope is that this teeny white hole could be either detected or some effect of them detected. And my great hope, I don't know if it's right, is that they could explain this strange, mysterious thing which is dark matter. The astronomers see dark matter, they see some matter which only interact gravitationally, and the best model is like a powder of teeny things. So maybe these are the white hole that quantum gravity predicts. So if this could work, it doesn't for the moment, but if this could come together nicely and we could pile up evidence for that, it would be an indirect evidence that the quantum gravity theory is right. So that's the way it works. Slowly, by looking at the consequences. I think that loop quantum gravity is right. I'm deeply convinced about that. 3 days out of 7 in a week.
I read it last night just to refresh myself before I interviewed, and I was completely convinced. But
Good.
I'm sure that's not a ringing accolade.
I think science, good scientists, and it's a person who changes mind often. If we look back at Einstein, you see why was he spectacular? And then you realize one thing, he's one of the scientists who did the largest number of mistakes than everybody else. He has written a number of wrong papers and said a number of wrong things, more than everybody else said. So he said, why? I mean, he was smarter, he was clearly more intuitional. Why did he make all mistakes? Because he was trying this, and every time it was not working well, just abandon it, go somewhere else. You know, the people who are really convinced of something and stubborn continue are not smart ones, they're stupid ones. I think the intelligent people are those who believe something and then they change their mind.
It's been a pleasure talking to you, Professor Carlo Rovelli. Thank you very much. And we know you've got to go now and talk to other people, so thank you for your time.
Thank you very much.
Really appreciate it.